Okay, I got my Slack channel open. If you got questions, put them in the chat, and Maricela will get them to me. We're on lecture number 5. We're building up to our first PDE, which is the heat equation. I'm going to have a lecture. Many students have said some of the background material is a little bit hazy for them, so I'm going to go through some of the stuff on linear ODEs, hopefully making it, as I've said before, a little bit interesting for the students that are up to speed, and useful for students that need the reminder. So here's where we're going to go Thursday lecture. After this, we're going to talk about the heat equation, which we derived last week. So that's got U of X and T as the unknown. And it satisfies a partial differential equation. So this is our first partial differential equation, arguably the easiest one to consider, which is why we're looking at it first. Okay, and the partial differential equation looks like this. Okay, and just in case you haven't seen this notation, this is notation for the partial derivatives. So here is the partial differential equation. Hang on here. And it's going to apply for positive time. So we're going to give some initial conditions and see what happens to the temperature later on with this internal forcing. And we're on this finite domain. This is this thin rod that we looked at the temperature distribution in before. If we're looking at the types of data that we have, here, let me get a different color. We've got already one type of data. This is this interior forcing. So this is data that will be given to us. It's describing the volumetric heating rate as a function of space and time in that rod. And there's a question that came through on Slack. Can we set some time to discuss homework number 1 and what the class struggled on? I'm going to say, I think it would be useful to delay that. Solutions to the assignment will be posted on Wednesday. So I'm not saying no, I'm just saying that might be better put until after you've had a chance to look at the solutions, just to see how things could go with the right skill set. And I think that'll put us in a better position to have that discussion. So if you're willing, I'll say let's wait until the beginning of Thursday's lecture, and then I'm happy to talk about that. I have heard from a number of people that this assignment was too long for a weekly assignment. I will certainly try and adjust that in the future. I mean, number 2 is already out, but I'll make some adjustments for assignment number 3. Okay, so we have other types of initial data for this problem, or other types of data. So we're going to have to say what the temperature of the rod was initially, right? Because this is a partial differential equation that describes how the temperature changes in time. But if you know how something is changing in time, you have to know something about its initial state to be able to use that. So I'm going to have initial conditions. Where's my blue? So here is another type of data that's going to be given. Of course, we can separate these problems. I'm going to remind you how that goes into subpieces where we see only one piece of data at a time. We're going to have Green's functions for all of these. And and series solutions that handle them, and so on. Okay, we're also going to have the temperature at the boundaries will be given. So I'm going to lump these together and call these boundary conditions. And so there's some more data. Okay, before I go on, let me just say what this is. So this is going to be an initial value problem, but it's also got boundary data. So you get to say an initial boundary value problem. And before I go on to break it up into pieces like you've seen before, but this is a good reminder, I'm going to say that one of the things you can do to write out a PDE like this is to make a nice picture. Right? So you're not trying to parse through what all of the symbols tell you about the problem. You can just look at this nice picture. So this is typically how PDE problems are presented in an informal way. You've got initial data down here at time 0. You've got boundary data on the two sides. And you've got the PDE here in this domain in the middle. So this is typically how, in a class setting or any kind of informal discussion, this is how you would do it. And of course, we've got these 3 types of data, right? 4 labels for data, 3 types. And just like we've done before, we can separate those out into 4 problems. I'll make a little table. You've seen this before. I'm going to have problem 1, problem 2, problem 3, and problem 4. And I'm going to get the solution. U will be the sum of these things. And in each one of them, they're simplified in that you only have to handle one type of data at a time. What are the data you've got? You've got U0, you've got F, you've got B0 and B1. Those are the boundary data. And so for the problem 1, you're only going to consider the initial data and set all the other stuff to 0. For problem 2, you're going to set the initial data to 0, handle the data, forget about the other ones, and so on. You'll look at each one of the pieces of data separately. Oh, there's a question. Is it important to know anything about the boundaries, whether they are isolated or not? And by isolated, you probably mean insulated. So these are not insulated boundary conditions. These are given temperature conditions. So this is in the literature, it's known as a Dirichlet condition. If you want a insulated boundary condition, that would say that du dx here at the boundary is 0. And how do I know that? Minus du dx, this is proportional to the heat flux. That's what we looked at in last week's lectures. So if a boundary is insulated, it means there's no heat flux going through it. And so I know this would be the boundary condition that I would put on there. Now, that's replacing this one. You don't get to put both boundary conditions. That's over determining the problem. There won't be a solution, but you can certainly replace it by other conditions. And we'll talk about that after the first go at the heat equation with the sign series. We'll look at other boundary conditions. There's also interesting things you can do where you can say there's like a Newton law of cooling term in which the derivative and the value have a relationship. And so that's all stuff that's coming up. Okay, so we're going to do two things next. We're going to take a step back and look at finite dimensional initial value problems. So it's going to be for scalar and vector U. And in that sense, there's no boundary conditions put in there. So we're going to look at initial conditions and interior forcing first in a simple setting. And like I said, this is going to be some review, but hopefully some new perspective on it. So stuff you've seen before, but maybe at a higher level than you saw it then. The other thing, which I really want to point out, which is a really important concept, which is that these two solution processes, I guess, are related. In fact, once you solve the initial value problem, you know what the formal expression for the solution to the interior forcing problem is. And this is something called DuHamel's principle. So I'll show you how that works in a number of situations. And one of them should be quite familiar to you. Now, maybe I should get a red pen and say all of this stuff, dividing things up into these subproblems and this DuHamel's principle, right? This is only for linear problems, right? Well, okay. Remember the first derivation we did was for the weighted stretch spring, which is which was a nonlinear problem to start with, but we looked at it around an unweighted case and could get a linear problem out of that. If ever you have some sort of base or equilibrium solution and you only change it a little bit, you'll end up with a linear problem around that. So linear problems are not that uncommon, and they almost always arise as some sort of approximation with some small change to a given state. Now the question is, how can you tell a problem is linear? At this stage, I think you should be able to look at a problem and say, okay, that's linear, that's nonlinear. If you've got something that's got a u squared in it, it's not linear. The only kind of linear things are, constants times a linear thing. And if ever you're wondering, just look and see if you can whether you have the superposition property, right? If you have two solutions, can you add them up and get a solution with the data that's added up, right? So if ever you're wondering, that's something you can check. Superposition, that's the big thing. Okay, so now we're heading into this review section. I'm going to start as basic as I can. Let's talk about scalar U of T. So we're back to a scalar U, and I can write out the initial value problem, a somewhat general one for a scalar U of T. It's U dot, okay, and the dot is for du dt. This is typical notation to help you remember that it's a time-like variable when you're looking at that derivative. And this is going to be given as a function U of T. So this is, in general, nonlinear. You can see the only kind of linear thing is going to come up later. So in general, that's a nonlinear problem. So let me tell you some of the theory of these things, just in case you didn't catch it there. If that right-hand side function is differentiable, and you can make this statement for this theorem with weaker conditions on F, but this is a good one. There exists a unique solution in an interval 0 up to some time. Because remember, for nonlinear problems, you can have only finite time existence. You can have things going off to infinity in finite time. And there's some good conditions in the notes which let you know when you know the solution will exist for all time, for sure. So let's restrict ourselves now to linear problems. Okay, so that's U dot is, now I'm going to allow for some time-dependent coefficients in the linear problem, plus F. So where's my blue? Here is the data. And here is a different type of data, right? So these are going to be given data. So I got two types of data. There's no PDE, there's no boundary value, so there's only those two in this simple example. So there are two types of problems. I got the problem number one, where I've got the initial conditions, but not the forcing. And I've got the second type of problem, where I've got the A of T U plus the F, but I don't have any initial conditions. And if I call this problem one, then the solution to problem one is just the sum of those two. Now, you've seen this before, right? This is something that should be quite familiar to you for linear problems. This is the homogeneous solution. And this is a particular solution. The only difference is, okay, and this is a little bit subtle. I'm not going to write anything down, but I'll talk. And if this makes sense to you and helps, that's all good, right? And if it doesn't, then you can forget about it. But typically, I'm looking for, in this way I'm writing them, I'm looking for particular types of particular solutions, if I'm allowed to say that. I'm not looking for something that just satisfies the equation with the F, forget about the initial conditions. No, I want to find a specific one, right, that satisfies these initial conditions. Whereas in Math 215 or whatever course you first had differential equations in, you would find this thing a particular solution and forget about the initial conditions, right? You would forget about these entirely, right? And then the homogeneous solution, you would then pick the constants in it to satisfy the initial conditions, including the fact that the one you picked might not be zero at the initial time. Okay, so the solution process you had in the past would have divided up this problem maybe a little bit differently, but it's not that much of a stretch to realize that this gives you definite value or definite functions for U1 and U2 that satisfy the two problems separately. Okay, well, let's remind ourselves how this goes. Let's solve problem one. This is a hint for the next assignment if you need a hint. there's a problem where it says find an integrating factor. So here's where we're going to find the integrating factor. Right, so I'm going to multiply this thing, the equation, by e to the minus a of t, where that capital A of t is the antiderivative of a. Okay, why did I pick this? Well, because a prime is equal to a, right? That's just the fundamental theorem of calculus. And I've picked the arbitrary constant so that it's 0 at time 0. Okay, so why did I do that? Well, let's look. So now I'm going to have e to the minus at u dot minus a of t e to the minus a of t times u is equal to 0. Okay, well, doesn't look any easier, right? Okay, but it is, right? Because now I'm going to recognize I multiplied by the right thing to make this a chain rule or a product rule derivative. This is just e to the minus a of t times u. Okay, well, and I can just check, right? Check that it works. I take the derivative. I have to take the derivative on the two sides separately. And so I've got, leave this exponential alone, I get this term. And then if I leave the u alone, I have to take the derivative of e to the minus a of t. And here's where I use the chain rule, and I get exactly the expression there. So now I can integrate. And I get e to the minus a of t times u of t is some constant. That gives me u of t is e to the a of t times some constant. And if I match the initial conditions, that's u of 0 is u0. That gives me u0 e to the a of t. Okay, so when I talk about the initial conditions for this problem, there's only one scalar value. And so I'm going to do something that's a little bit unusual. This is not what people usually say in words. But I'm going to call this thing here, I'm going to call this the Green's function for the initial conditions. Okay, well, why? Well, there's only one initial condition, one scalar value. So I don't have to integrate over anything or sum over anything. There's just one. And how do I get the solution to the initial value problem? I take that data and I multiply by that function and I get the solution, right? So this is really telling me how the initial conditions affect the solution at all time. That's a pretty interesting thing. Now, I'm going to go on to problem number 2. And we're going to see that the solution process is similar. And the Green's function for that one, which will be a function of 2 variables, because I have to figure out how the f at every time affects the solution at every later time, right? I can really get that from this Green's function in a simple way. And this is what DuHamel's principle is. It basically says, once you know how the solution to the initial value problem behaves, then you know how the solution to the interior forcing problem behaves. It's just an integral of what you found before. And this is a very general thing. Again, only for linear problems. Okay, so here I've got the no initial conditions, because I've already solved what happens with the initial conditions. There's a question asking me to repeat the reasoning behind calling this thing the Green's function of the initial conditions. Well, okay, so remember we've only seen one Green's function, or two if you count the one that you worked out in the assignment. But remember, it's the map from the data to the solution, right? And if you have a continuum of data going to a continuum of a solution, right, then you have an integral over the data giving you the value at every point. That's the kind of Green's function we had before. This one, people don't usually call a Green's function, this a Green's function. So that's fair, right, to say you want me to explain it again. But this has exactly the same property, right? There's only one data point, right? It's just whatever the scalar U0 is. And you want to know the map of that to what the solution value is at any time. Well, this is exactly that, right? You take the initial data, you multiply by that function. So this is really the map from the initial data to the values of the solution. It's a stretch. No one else in the world would call that a Green's function. I've never seen it before, but it's generalizing the same idea, right? Okay, I got an okay that sounded good. So I'm going to play the same game I did before. I'm going to multiply by the same integrating factor. And do some of the same work that I did before. So I'm going to get the time derivative of e to the minus a of t u of t. And now I've got something on the right-hand side though. Okay, and then I'm going to integrate this from 0 to t, and I'll use the s as a variable of integration. So I can get a Green's function g of x of s and t, just like I had a Green's function g of x and s in the boundary value problem. Okay, so I'm going to integrate this derivative. So I'm just going to get the difference in the values at the two ends, but the initial value for u is 0, so I won't see that. I'm going to get e to the minus a t u of t, right? And now, well, here I really have to integrate. So I'm going to get u of t is the integral from 0 to t, e to the a of t minus a of s, f of s ds. Okay, so now it's not so much of a stretch, right? Now this is looking like the Green's function we had before. We got t instead of x. That's the only difference. So here's the Green's function. Again, it's the map of how the forcing affects the solution. And of course, there's some interesting things we can see right away, right? One is we've got the causality thing, right? Only depends on f of s for s less than t. So causality. Right. It's just so interesting how you sort of make slight changes to problems you write down, and and the mathematical properties change so much. But of course, remember, we're writing down things that describe physical and financial, problems, models. And there's all kinds of different behavior that happens in those things. So it's not surprising that we see different things as we look at these problems, even though they share the same kind of mathematical language. Okay, the other thing I want to do is really look a little bit more closely at this thing. Remember, this is the integral from 0 to t a of s ds. Oh, now I better use a different dummy argument. I'll do a of tau d tau, right? And so if I subtract these things, I'm just going to get the integral from s to t of a of s ds. And I'm going to look at this a little bit more closely again. Oh, there's a question. Finance can be described using the heat equation. As I mentioned, if just depending on how the course goes and the interest of the students, we will have some time at the end where we'll talk about free boundary value problems. One of them comes from math finance. It's called the Black-Scholes problem. Well, there's more going on than just the heat equation, but that's part of it. The heat equation has a relationship describing some probability things. If you think of thermal diffusion as coming from sort of random molecular motion, so there's a probability connection, and that's where the finance connection comes in. Okay, I'm going to look at this. This is actually the Green's function for problem 1, right? Which was just the initial data problem, not the forcing, right? So this is the Green's function for the interior forcing, the F, but I'm telling you that the thing that appeared is exactly what would come as the Green's function for the initial data, but with the initial data at time s. So if you want to understand how the interior data affects the solution, it's like, well, it's an integral, not just a function. But the flavor is it affects the solution like initial data of size f would affect the solution if you applied it at time s. So this is the example of DuHamel's principle, which says if you understand the initial value problem, then you know how the forcing enters the story. Okay, let's do an extremely simple example to make sure that everyone is on the same page. I'm going to have a constant coefficient one because that makes the algebra doable. Normally, for any kind of differential equation with interesting systems. Okay, there's a question coming up with, would I call that, would that be like a memoryless system? Well, no, right? because remember, there's initial conditions. It remembers the initial conditions because this is only part of the solution. You have to add in the initial conditions. Every F affects the solution at all later times, right? There's memory, right? There is memory. Now you're going to see something coming up where you will see that some of the memory gets forgotten if you wait long enough. You know, dementia kind of sets in. So let's go through this example, and I can show you at least that idea. So I'm going to give initial conditions. I've got an F and initial conditions. Okay, the first initial value thing, that's pretty easy. It's just this, right? Okay, right. You can see that, and the second one would then be the integral from 0 to t. And now I'm going to have this thing, right? Cosine s ds. This is this integral. And now you can use Math 101 techniques, or I used Wolfram Alpha just because, like, why not, right? Sitting right in front of you.
You could also use complex analysis if you wanted.
Okay, there you go. You could.
I mean, you had to take it for this class, right? Don't waste it.
Wolfram Alpha would be my recommendation. That's one of the things we're gonna have with the format, which is interesting, right? To think you know, COVID conditions have you know, kind of driven me to, you know, kind of assignment heavy weights on the grading scheme. But it's exactly working through longer questions on assignments that should be assessed in this class, and doing, you know, Math 101 integrals. Okay, that I don't need you to know how to do that. It's the next sort of phase. And so that really has opened up some good opportunities. And I was talking about this with someone the other day. It's like, okay, if I teach this class next year, even if it's face to face, this seems like a much better assessment policy than otherwise. Anyway, however you do it, if you do this integral, here's what you get. Right? And you notice that this term has the same form as the homogeneous solution. So what I was saying before is, if you did the method of undetermined coefficients, you would have just found this particular solution. And then the homogeneous solution would be a little bit different. Okay, to match the initial conditions, but you'd end up with the same solution, which is 1/2 sine t plus cosine t plus 3/2 e to the minus t. Okay, so there's two parts, right? There is the particular solution and the homogeneous solution, which, you know, is divided up, like I say, slightly differently in the process that we use to get it. But this should be familiar. Let's just talk about this a little bit more, though. This is a solution that has damping, right? It has solutions that, without forcing, that's this only initial conditions. Without forcing, the solutions decay exponentially, right? So here is the influence of the initial conditions decaying exponentially. So we could call this a transient. Right, and after the transient from the initial conditions, all we see is this thing. Now, if the solution tended to a solution after the transient that was not time dependent, we would call it a steady state solution. Well, this solution after the transient does have time dependence. So it's not really quite right to call it a steady state solution. You could, I'd be okay with it, but many other people wouldn't. So I will say, instead of calling it a steady state solution, I'll call this the persistent solution. Persistent, ENT, ANT, I don't know, I'm gonna guess.
ENT.
Okay, 50-50 chance and I got it right, thank you. So okay, there's a question that comes in. Would it be possible to go over Green's functions in more detail at some point? We briefly covered them at the end of lecture 2, but for the vast majority of us, it's brand new material, and all this talk about Green's functions has been a bit confusing. Well, I'm going to show you some more Green's functions, and I hope that'll give you the idea. Along the way, I've given you sort of step-by-step instructions for how to construct them and the properties that they have to have. I think as we go through the lectures and you work through the assignments, you'll get the idea. But if not, yeah, I will definitely come back and have another pass. Hopefully, this stuff looks familiar, right? The solution process should look familiar, and all I'm doing is attaching some labels onto things that you've seen before. Okay, so we've looked at the scalar case. We're aiming for the heat equation. Let's take an intermediate step before we go to the heat equation. So let's talk about how this all looks for vector linear problems. So this is going to be an n component vector. And I'm going to do some matrix multiplication of it. So I guess I want to tell you it's a column vector, just so you have a concrete picture in your head, right? And I'm going to have a linear system for this. With initial conditions. So I'm going to do the two problems again. I'm going to set f identically equal to 0 here and just look at the pure initial value problem. Now, you've only seen it once, as the student in the question pointed out, and so it's not like I'm expecting you to get this right away. So we're going to see another example, right, where we're going to work out without concrete details for a particular problem, but how the solution process works, taking the initial conditions and giving the solution from it. It's going to be a matrix, which is a function of t times the initial conditions. Will give you the solution at all later times. I'm going to call that a Green's function, even though typically in the literature, that's not what it's called. I'm going to show you that, and then show you how DuHamel's principle also applies in this case. So I'm just going to say, hey, what if it worked the same as it did before? And then I'm going to show you that it does work. Okay, so it's something which I'm not just going to ask you to take on faith. And I think once you've seen the details a few times, you'll see how the game goes. And then at some point, I don't want to just give the general theory all at once. I want you to see some examples. So at some point, I'll give you the general statement of DuHamel's principle, which is a little bit abstract. So not as useful in this case. Okay, so I'm going to say I expect the solution to the pure initial value problem, U of T, to have the form. Well, I want to get U of T. I know it depends linearly on the initial conditions, right? If I multiply U0, this whole vector by 2, then the solution will get multiplied by 2. And let's just remember, this has n components. This has n components. And you know that each component of the solution is going to be affected by each component of the initial data in general, right? If the matrix A was a diagonal matrix, that wouldn't be true. But okay, we're not just looking at diagonal matrices, right? So there's going to be a matrix, right? This is going to be an n by n matrix. And it's called the fundamental solution matrix. Okay, and you could call it a Green's function because it's a map from the data to the solution. Okay, well, okay, this works. If every column so I'm going to have the jth column of the matrix, right? So it's a vector, satisfies the differential equation with initial data that's one of the standard basis vectors. This is basis vector unit standard unit basis vector. Okay, well, so let's note. Right, okay, well, solutions to these problems are unique and guaranteed to exist. So I can solve for each of these columns of this matrix. And my claim is, if I put it all together, right, that I will get something that solves any initial value problem. Okay, well, you're solving the initial value problem for a basis for the initial conditions. So of course it makes sense that if you put all that together, you're going to be able to do this. So let's note a few things. If I look at this matrix at time 0, right? Well, all of the columns are the standard basis vectors, right? So this is going to be the identity matrix. Right? Okay, so I got that. What's the other thing I know? That if I take the derivative of this matrix, right? It's going to be, well, this is an n by n matrix. It's going to be the matrix A times this matrix. Well, I just look column by column. So now I want to use those properties to show that what I wrote down really is the solution. So if I take du by dt, and this is from this thing. This is going to be, well, it's going to be the time derivative of this matrix times the initial conditions. This is what I say is the solution. Well, this doesn't depend on time, so the only time dependence is here. So I'm going to have the derivative of this matrix, but I've just worked out that that's just A times the matrix. Right? And this is what from 3 I said was U of T, so this is just A times U. And so I've shown if I put all of this together, if I make a matrix by solving this problem for any initial conditions, right, in the standard basis, I put it together column by column, I can get any solution with any initial data just by multiplying by that matrix. Now, again, there's some things you might have to wrap your head around, matrix vector multiplication, but at least you know that if you're looking for how the initial data affects the solution in a linear problem, right? And you have this idea of superposition in your head, and you know how each of the components in the initial data affects the solution, then it's just a question of doing the right kind of linear combination of the effects from all of the components of the initial conditions to get the solution, and that's exactly what this does. Okay, I'm going to give you a minute to digest that. Fundamental solution. Okay, so now I'm going to go on to problem number 2. This is where I have no initial conditions, homogeneous initial conditions, but I'm going to put the forcing back in. And I'm going to extend the previous idea to have a matrix that's a little bit different looking. This is now going to be the fundamental matrix. But with initial data at time s. So there's a few things I can say. If I look at this kind of generalized thing, I just get this one that we had before. Right, so if I have the initial data at time 0, I'm going to get the same matrix I had before, right? The other thing I'm going to know is that if I take the time derivative of it, same reasoning as before, it's going to be A times the matrix. And this is going to be true for every S. No matter where I start, I'm solving the differential equation. The other thing which I want to have is if I look at the map from initial conditions at time t to values at time t, I'll just get the identity matrix. I haven't solved the problem anywhere. I'm just spitting back the initial conditions. This is exactly like this guy at time 0 is the identity matrix. Okay, so remember I talked about DuHamel's principle. We've seen it. We've seen one example, right? That's where if the problem is linear and it's an initial value problem with data, but I've solved the initial value problem alone, then the solution of the oh, there's a question coming up, maybe. If it doesn't get answered by the audience, I'll pick it up. I'm going to say, I'm going to tell you that this is a general rule. Oh, the question is, I don't understand what this new matrix is. This is the same as the old matrix, except I'm allowing initial data, not just at time 0, but at other times, right? Time s, right? So if I gave initial conditions at time s and solved the problem, this is the fundamental matrix that would come up, right? So DuHamel's principle would say that if I want the solution of the, this is with problem number 2, right? Roman numeral 2, with U0 equals 0, but F is in. The solution to that problem, I'm going to have a Green's function, which will integrate over the data. And the one that I'm going to use is exactly this thing. How the forcing enters the solution is as an integral of how initial data at that time would affect the later solution. Now, I just wrote this down, right? It's pretty optimistic to think, oh, that is going to work, right? So now we need to check. I've just written this down with no warm up that this is the right thing to do, except motivated by the scalar case. So I have to take the time derivative and see that it satisfies du dt with this formula. Du dt is a times u plus f. So let's calculate the derivative and see what comes out. Well, I've got t in 2 places. This is a similar game we've had with Green's functions before. So I have 2 places I have to take the derivative. I have to take the partial derivative inside. And then I have to evaluate it at the upper end. This is the fundamental theorem of calculus. So this is psi t times f of t, right? And this is the identity matrix. So this is just f. Well, that's promising, right? I'm supposed to end up with a times u plus f on this right-hand side, if it really is the solution. Here, I'm going to use the this property. Let's see if I can fit that in. So this is going to be the integral from 0 to t. Now this is a of t times psi f of s ds. Now I can pull this out. And I see I've got exactly what I want. This is what I've defined to be the solution optimistically. And so I get a times u plus f, right? So this is all very formal, right? But it works, right? This is the solution, right? If you come up with this matrix with these properties, you can get the solution to the problem with data from this formula. Okay, and I'm going to say, remember one of the polls I had last week was how familiar are you with the variation of parameters formula? This is the variation of parameters formula. I think it's the way the variation of parameters formula should be taught, instead of the confusing thing that you probably got in Math 215. Okay, now I'm going to look at the time and go in the written notes. It's something that I thought was interesting. And if you ever wondered where that crazy variation of parameters formula came from, this is a very nice way to see where it comes from in a more logical way. So I'll say see the notes for this. Let's say interesting. I think it's interesting, but not essential topic. Okay, and with my remaining time, I want to look at the simplest case. Right, of u dot is A times U. I'm only writing down the initial value problem because now we know once we solve that, we've also solved the forcing problem with DuHamel's principle. And the simplest case is where A is symmetric and does not depend on time. And remember, when we had the heat equation, we've got the UXX with boundary condition terms, which was symmetric and didn't depend on time. And so this is really the bridge to the heat equation term. So A has real eigenvalues. I'm looking at the time. I got 10 minutes. I should be able to do this. Oh, there's a thing. So we treat any forcing functions as a continuous superposition of an initial conditions almost. Is that an acceptable way of thinking of it? That's exactly what we've shown here with this DuHamel's principle. In the two and only two examples that you've seen it in, but it's a general way of looking at problems. Yeah, that is not only acceptable, that is a very nice way of putting it, more nicely worded than I had done myself in my lecture. So thank you. Okay, so we're looking at this game now in this case with some simple simplifications that we can make. We've got real eigenvalues, and we've got orthonormal, ON for orthonormal eigenvectors, VJ. Okay, and remember, I've got n of these things, it's a basis. Right, so that means I can write any vector as a linear combination using these guys. So without any relevance to the differential equation yet, I always can write a vector. So at any time, I can write the vector as a linear combination of these eigenvectors. Okay, and this is for some functions, some coefficients. Okay, and I'm going to show how you match the differential equation by picking those coefficients correctly. But let's just match the initial conditions first. So to match the initial conditions, I would need the sum for these coefficients at time 0 to match the given initial conditions. So this is the same as, well, when you're trying to figure out what linear combination of vectors gives you another vector, that's a linear system, right? And if you have a linear combination of column vectors, that's the matrix of the column vectors times the column vector of the coefficients. So I'm going to make a matrix T, and this is the Vj vectors in the columns times the coefficients at time 0 is the initial conditions. And so formally, I can say I multiply by the inverse matrix of the eigenvectors in the columns times the initial conditions. Okay, and just as a note, if the columns of T are orthonormal and a basis, then the inverse matrix is just the transpose. Okay, so there's a nice property here. Okay, and how does that go? Well, when I multiply matrices in my head, I take the row of the one on the left and I turn it sideways and I take the dot product with the things. So if you take T transpose, that has the orthonormal vectors in the rows instead of the columns, right? Because the transpose changes rows and columns. So if you take that matrix and you've got these vectors that are orthonormal in the rows and you're taking the dot product with the vectors that are orthonormal in the columns, then you'll get the identity matrix. And so that's why the inverse is this transpose. Okay, what's the next thing I'm going to do? I'm going to take this expression and I'm going to put it in the differential equation. Right, so I'm going to have the time derivative. So I had Aj times Vj. When I take the time derivative, I'll just take the time derivative of the coefficients. And over here, I'm taking the sum of the same things, but I'm multiplying by A, and these are eigenvectors, and so I just multiply by a scalar lambda j, right? And these are orthogonal. So if the two sides are going to be equal, then the coefficients have to be equal. So that says Aj dot is lambda j times Aj. Oh, well, that's an easy one, right? So now all of these guys separate. And I get separate exponential solutions for all of them. And I can put this together and say, this is the same thing as writing the vector A as a very simple matrix. This is the diagonal matrix. With entries e to the lambda j t. And this thing is the same thing as this T transpose times U0. Okay, and now the solution, U of T, is, well, I want to make the solution, it's just this sum, right? That's just the linear combination of column vectors, same argument we had before. It's this matrix T times A of T, and that's the matrix T, diagonal matrix with the exponentials in it. T transpose, it would be T inverse in general, but in this case with the normal eigenvectors, it's the transpose times the initial conditions. Oh, well, this is the matrix that you multiply the initial conditions by, matrix that depends on time. The only place where this depends on time is in here, right? With the exponential terms on the diagonal, right? Right. You multiply by this matrix to get the solution. So this is the fundamental solution. Phi of T that we talked about before, right? And in this case, we can label this as e to the a t. If you look at the power series for the exponential and you put in matrices, you get exactly the same thing as that, and it has all the properties of an exponential. Okay. Okay, so 1044. I think this is a good place to end. There's a little bit more in the notes, which is going to line up with how we're going to look at the heat equation. We're going to look at the heat equation initial conditions, and then we're going to look at the forcing, and we're going to show that we're going to have the same kind of story with DuHamel's principle. We'll be able to formally get some expressions for the Green's functions that won't actually be that useful. It'll be the series solutions that are going to be the ones that are going to tell us the most in that situation. Well, that'll be our Thursday's lecture. And then we'll look at some of what happens as you change the boundary conditions to some of the things that were mentioned earlier this lecture. If you've got insulating or Newton's law of cooling type boundary conditions, how do things change? And there's one of those on your next assignment as well. Okay, that wraps up today's lecture. I'm going to stop recording, but I will stay on the line for the next well, half hour, or until you guys get bored, or until I get too hungry, whatever comes first. And otherwise, I'll see you all on Thursday.